Welcome to EDU World Space.
This is chapter 21, problem number 42. We're given 2-point charges and we're asked to calculate the net electric fields at point A and B. Let's start with the point B. So at point B, we have two electric fields superimposed, right? First coming from the positive Q to the left, and then the other field coming from the positive Q on the right. To be able to distinguish the charges, let's give them let's call them Q1 and Q2 for now. Now for the net field at point B, let's see what we have, right? So assume that the line that connects them to each other is x equals 0. And then we have A that is going through, well, this is the y-axis. And then we have the origin here. So now we're at point B. Let's figure out the direction of the electric field due to the first charge. It would be, since it's a positive charge, right? The electric field would be pointing along this line that connects Q1 to point B. So this would be the direction of E1, right? So you see this triangle here. We know this distance is 5 centimeters, and also this is 5 centimeters. Then let's call this distance from Q1 to B R1. Then R1 is going to be equal to, right? This is 45 degrees, obviously, because we have 5 centimeters and 5 centimeters, so that leaves us no option. So theta 1 is 45 degrees. R1 is going to be equal to then 5 squared plus 5 from the hypotenuse square root of this, right? So then that is going to be equal to 5 square root of 2. How can we write this E1 vector? Then E1 vector, the x component of this E1 vector is going to be equal to E1 times cosine 45. It's in the I hat direction. For the y component of this vector, which is pointing up, which is E1y, right? It's going to be E1 times sine 45 j hat, where we know E1 is kq over r1 squared, cosine 45 I hat plus kq over r1 squared sine 45 j hat. All right, let's leave it at that. Now let's switch to E2, okay? So E2, again, this is a positive charge. E2 would be along this line that connects Q2 to point B. So E2 looks something like this. Again, well, the angle here is now theta 2. And how are we going to determine this theta 2? You see this triangle here that has, in order to calculate what theta 2 is, what we can do, we can look at the tangent of theta 2. Tangent of theta 2 is going to be equal to 5 over 15 here, right? 5 over 15, 1 over 3. Then theta 2 from E here equals to 18.4. 18.4. And let's see what this distance R2 from the point that we have the second charge to the point B. So R2 squared again, well, let's not calculate the square, let's just calculate R2 from the Pythagorean theorem, right? We have 5 squared plus 15 squared, square root of these two. Square root of 15 is 225. So then this is square root of 250, right? When you do the algebra here. Now, let's write what our E2 is then. E2, again, this is the x component, and this is the y component of E2. And this angle is also theta 2. So then E2 is going to be E2 times cosine of 18.4 negative I hat, because it's in the negative x direction, plus E2 sine 14.4 the y component is j hat positive because it's in the positive y direction. Now let's remember what E2 is. E2 is, the magnitude is kq over r2 squared. Let's substitute for E2, kq over r2 squared cosine 18.4 negative I hat plus kq over r2 squared sine 18.4 j hat. So this is 18.4 here. It's a little crowded in here. I apologize for that. All right, so now we know the E2 vector and E1 vector at point B. In order to calculate the net field EB, then what we need is we need to add these two vectors to each other. So E1 was kq over r1 squared cosine 45 I hat plus kq r1 squared sine 45 j hat. E2 is kq r2 squared cosine 18.4 negative I hat plus kq over r2 squared sine 18.4 j hat. Now let's group the x components. Kq over r1 squared cosine 45, right, minus kq over r2 squared cosine 18.4. This is the I hat component plus kq over r1 squared sine 45 plus kq over r2 squared sine 18.4 j hat. Now we separated the x component and y component. Well, let's do our calculation then. So here, kq, we have kq, right? We can take this out, and then write this as cosine 45 over r1 squared minus cosine 18.4 over r2 squared. And then we have kq on the second term too, so let's bundle, right? Let's say I hat here plus sine 45 over r1 squared plus sine 18.4 r2 squared j hat. All right, now we can plug in our values. So k equals 9 times 10 to the power of 9. Q is 5.7 microcoulombs, so it's going to be 10 to the power of 6, negative 6 coulombs. And then we have cosine 45. I'm going to leave as is. You can figure out what it is using your calculator, right? And over, we have r1 squared. R1, if you remember, it was 5 square root of 2. But this is in centimeters times 10 to the power of negative 2 meters squared, right? And minus what we have here, cosine 18.4 over is a distance r2. We had found it to be square root of 250. Again, we need to convert this to meters squared. This is I hat, right? Now we have the y term, so we're going to have plus, right? Sine 45 over 5 square root of 2 times 10 to the power of negative 2 squared plus sine, pardon me, all this kind of today's work, sine 18.4 over square root of 250, but again, we're converting it to meters square. This is j hat, right? All right, from here, we're going to find the overall vector to be 5.3 times 10 to the power 6 I hat plus 7.89 times 10 to the power 6 j hat. Then we have the EB vector, right? The electric field vector at point B. How are we going to calculate the magnitude is just we're going to take the square of the x component of this and add that to the square of the y component and take their square root. So the magnitude of EB is going to be 9.5 times 10 to the power of 6 newtons per coulomb. And the direction, in order to get the direction, tangent theta equals EY over EX total, right, at point B. Then the inverse of tangent EY over EX is going to give us the angle. Then that would be equal to 7.89 times 10 to the power 6 over 5.3 times 10 to the power 6. So from here, the angle can be found as 56 degrees. All right. Now, we answered the first part of the problem. The second part is asking, remember, asking for the net field at A. This, which is easier. So, let me draw it again. This is where, well, we called it Q1 and Q2 is, this is point A. This distance is 5 centimeters. The distance from here to there is 10 centimeters. The beautiful thing here is that the charges, each charge is equidistant as far as the point A is concerned. If one is r away from it, so is the other one. Because, as you see, we have identical triangles here, right? So then the angles are going to be the same. So actually, even the magnitude of the electric fields are going to be the same. So the electric field due to the first one is going to be pointing this way, right? And the electric field due to the second one is going to be pointing this way. And they're going to have the same magnitude. A is going to be equal to KQ over R squared because now R's are the same, right? This equals E1, that equals E2. Therefore, you see the shortcut here? The x components of these fields, EX, they're actually canceling each other out. One is in the positive x direction, the other one is in the negative x direction, which means we're left with twice the magnitude of the y component of this electric field, right? So then the total field at A is actually twice of EY, and you know that it's up. So you know that the overall angle that the total field makes is going to be 90 degrees because it's purely up. So let's calculate what E sub y is here. In order to answer that, obviously we have to find what this angle is here, right? So the angle can be found using the tangent. Tangent theta is going to be equal to 5 over 10, right? It's 1/2, so that tangent inverse 0.5, meaning 1/2 equals theta. From here, theta can be found to be 26.6 degrees. All right. Then E sub y is going to be twice the electric field, total electric, single electric field due to 1 point charge times the sine of 26.6, right? Because if this is theta, then this angle has to be theta, then the sine of it is going to give us the y component. Let's remember what E was. E is KQ over R squared, sine 26.6. Let's calculate what this R is from the Pythagorean theorem. R equals 5 squared plus 10 squared square root of this, right? So it's basically square root of 125, right? 10 square root of 10 is 100, and plus 25. Then from here, twice 9 times 10 to the power of 9, 5.7 times 10 to the power of negative 6 coulombs, sine of 26.6 over square root of 125 centimeters. So let's convert that to meters. Then it's going to be equal to 3.7 times 10 to the power of 6 newtons per coulomb. And then what is the direction of this net field? It's up, which means the angle theta A is going to be 90 degrees. All right.